So we will go right away to the next and last talk of this session. And it's about a fascinating topic. There was a paper published in 1996 by Ch1 and Mark Richards about the differential rotation of the inner core compared to the core. And this is the topic of this paper, of this presentation. The title is Image Earth Inner Core Fine-Scale Heterogeneity and Temporal Changes Using IMS Arrays by Guaneng Pang. Please play the video. Thank you.
Hello, everyone. Today, I'm going to talk about how we use the IMS arrays to study the Festsaal structure of the inner core, the very heart of our Earth. This is what we currently know about the inner core. I call it, it is a standard inner core model. The inner core is a solid board with a radius of like 1,200 kilometers at the center of Earth. It is composed mainly by iron and nickel alloy with a few light elements. Seismic evidence reveals that there's seismic anisotropes in seismic velocities. And more interestingly, it can be roughly divided into two hemispheres, with the eastern hemisphere having faster seismic velocity and stronger attenuation. And perhaps most famously, the inner core rotates at a different speed compared to the rest of Earth. One question you may ask is that, why study inner core at all? After all, it lies deep beneath us, in a place we will never physically reach in our life. But the inner core does matter. It is believed that the heat released during the inner core growth drives the liquid outer core convection, which in turn powered the Earth's geomagnetic field, so that the Earth can exist on Earth. And the Earth's inner core also serves as a really important reference for under-territory planets, such as the Mars. If the Mars is the inner core, and what's the Mars inner core like? Does it look like Earth? We don't know. Since we can't directly sample the inner core, seismic waves are a powerful tool to imaging the inner core structure. Two types of seismic waves are used. The pk-IKP, which are the seismic waves reflected on the inner core boundary. And another one is the pk-PDF or pk-big IKP. It is the seismic wave passed through the inner core itself. One seismic wave encounters small-scale variations in velocity and density. They scatter around. These scattered energies arrive at seismometers either before the direct arrivals or more often after the direct arrival, forming a long chain of the seismograms. We call it coda. It turns out the inner core is far away from the homogeneous. If we zoom in at scales of just 1 to 10 km, velocity variations exist. These variations will create scattered wave fields that arrive later than the critical pk-IKP refractions, producing what we call pk-IKP coda. The figure here shows an example waveform through core at ILA. You can see that the amplitude of these pk-IKP coda is extremely small. They are only on nanometer scale, which makes them really difficult to be detected with only a single seismometer. That's why we need to use the small aperture seismic arrays to improve the signal-to-noise ratio. The figure on the right here shows array geometries for each array used in these studies, with the IMS arrays highlighted in blue. Previous studies were restricted to small regions. But the global deployment of the IMS array provides a really excellent opportunity to build a global pk-IKP dataset. Then we can map out the global inner core fine-scale structure as the map shown here. As the map shown here, the IMS dataset gives us broad global coverage, including a lot of regions that have never been studied before. Panel A on the right figure here shows an example PK-IKP coda observations from the region E8. The coda has a spindle-like shape. The energy grows gradually, peaks, and then decays. This shape reflects the inner core heterogeneous structure. By measuring the growth, decay, and the total duration of these coda, we test whether hemispherical patterns, like those we have seen in attenuation and anisotropy, exist in the inner core 5-scale structure. The answer is no. Instead, we see strong regional variations, but there is no systematic hemispherical difference. By modeling the PK-IKP coda, we can estimate the seismic scattering strength in the inner core. The figures here show the global 3D inner core heterogeneity structure we obtained from the IMS array observations. The maps on the left show map views at different depths, and the figure on the right here shows a depth profile view from the North Pole. Darker regions indicate stronger scattering and greater heterogeneities. There are some key points we need to notice. The first one is that you can see the scattering is presented everywhere. It has strong regional variations, and the most importantly, the scattering strength increases with depth, which means the deeper inner core is more heterogeneous. This depth dependence tells us something about the inner core growth. The stronger scattering at depth cannot be explained by the classical inner core growth model, which states that the inner core has gradually grown today. Instead, it's just a phase of rapid growth early in the inner core history, likely tied to the delay in nucleation caused by the supercooling. The core did not crystallize intermediately at the solidus, but supercooled until it overcame the nucleation barrier. Then it grew rapidly to hundreds of kilometers in thickness within thousands of years. After that, it gradually grew until today, but some liquid will trap inside the inner core and then gradually freezing. By comparing our scattering results with porosity models, we infer that the inner core nucleation was delayed by about 0.07 to 0.12 inner core age, involving supercooling of 20 to 30 K. Here, the inner core age was calculated from the moment when the core temperature dropped down to the solidus. The inner core differential rotation, it is one of its most debated properties. This idea was proposed over 30 years ago, but then debates continues. Indeed, there is observations that there's change in the inner core seismic waveforms, but people has been arguing about these changes are caused by non-rotational changes like the inner core boundary change, not the inner core superrotation. Here, using the PKB-IKB coda, we analyze the earthquake doublets. An earthquake doublet is a pair of nearly identical earthquakes separate in times. There are PKB-IKP waveforms, so intermittent changes. The figure here shows examples from ILA. Clearly, only the earthquake doublet in between 2002 to 2009 saw changes in PKB-IKP waveforms, not that doublet from 2004 to 2017. When looking globally, the picture becomes more clear. Each line in the right-hand plot represents a doublet, with the red indicate PKB-IKP change, and the blue indicate the no change in PKB-IKP coda. Panel A shows the polar rate path, and panel B shows the ectotic ones. Only doublets spanning the time 2001 to 2003 display changes in PKB-IKP coda, and the polar seismic rate path shows largest effect. This is expected from the differential rotation, since the polar ray paths are most sensitive to the change in inner core relative to the Earth's west to east rotation. So this suggests that the inner core experienced a burst of differential rotation during 2001 to 2003. Before and after that, the differential rotation was small, tiny. But what happened after 2003? We expand our dataset to 2023 and focus only on polar ray paths. We find that the PKB-IKB coda from 2002 to 2009 saw changes as shown in the black and red waveforms in this figure. But then by 2022, the waveforms match again as shown in the blue and black here again. This indicates that the inner core rotates back to the same position. By investigating the time spanning from those earthquakes doubling showing no PKB-IKB changes, we found that the inner core super-rotated from 2003 to 2008, and then sub-rotated 2 to 3 times slower back to the previous position. Even more, we find evidence for non-rotational changes. As the waveform show here on the left, some doublets after 2004 saw waveform change, tiny waveform changes in array YKA, but not on ILA. According to the rotation model we proposed, and these waveforms should follow the red star on this figure here and should not have changes on PKB-IKB waveforms. Yet, tiny waveforms changes occur on only YKA. The seismic ray path to YKA samples shallower than the seismic ray path to ILA. This suggests that only the shallow inner core has structural changes. Perhaps the whole shape of the inner core is distortion. These are discoveries we have made about the inner core using the IMS arrays. All works have been published. Please go through our papers if you are interested in details. Thank you very much.
Thank you very much, Guaning, for telling us about this fascinating topic. So one question that we have is, what is the relationship between this differential rotation of the inner core and the geomagnetic field? Can you expand a little bit on that?
Yeah, I mean, the answer will be like, I think there's still a lot of unknown of the detailed relationships, because like, for sure, people now believe that it's the inner core drives the outer core convections, but mostly it's from the heat, from its cooling. But for sure, one like the inner core is differential rotated, or even it has some like, or it's straight changing, so it may in some way to change the patterns and outer core convection that will ultimately affect our geomagnetic field. But for sure, it needs more jobs and more combining the geomagnetic observations, and even more high performance modeling, and then a more detailed models of inner core decadal changes to help us answer these questions more clearly or like more detailed. Yeah.
So is it envisionable to have a very complex model that would at the same time model the rotation and the geodynamo?
Well, I mean, I can see that there's some possibility there. If we can at least from our seismic side, we need to provide an accurate model first, right? I mean, we need to have an accurate differential model first. Then the people like geomagnetic field people can use it in their simulations. So yeah, I can see there's some potential here, but also there's a lot of effort we need to do like in this topic too. I mean, especially like the resolutions and timing here. Yeah.
Okay, thank you very much. Again, fascinating topic.
Yeah, thank you.
Thank you very much, Wan-Ning, and thank you very much to these 7 authors for outstanding presentations. We believe that it has been a great start of the scientific sessions of Science and Technology. And now we are going to move to the poster sessions. If you are interested in posters related to waveform technologies, please stay in this channel, channel 1. There will be poster presentations about seismics, hydroacoustic, and infrasound contributions. If you're interested in other topics, for example, radionuclide, on-site inspection, global challenges, outreach, and others, please move to channel 2. You will see on the left side of your screen that you can choose between channels 1, 2, 3, and 4. So I repeat, we will now take a short break of 5 minutes. If you are interested in waveform technologies, stay in channel 1. If you would like to listen contributions about other technologies, move to channel 2. See you in 5 minutes. Thanks a lot for watching, and let's have a great Science and Technology 2025 conference.